Hello, we are here with another demonstration of segment routing technology. This time we will show how SRv6 can be used to replace the user plane GTP protocol and what are the advantages of such an approach. GTP is the #1 protocol used in the mobile environment, although there are several versions and types of it. Here, we will focus on the GTPU that is used to encapsulate data in order to transport it over service provider network. GTP stands for GPRS tunneling protocol. So this protocol has been around for some time already and so has a few limitations. In December 2017, 3GPP established a study group to evaluate potential replacement for GTPU, and SRv6 is one of the options. Here, we will demonstrate how SRv6 can be used instead of GTP, or rather, we will show a possible translation or GTP into SRv6. Once we have in an SRv6 packet, we can use all the SRv6 features and functions on it. For example, we can load balance per flow, we can load balance per different server, and we can do any form of traffic engineering or service chaining. Here, we will demonstrate network slicing to create different slices in mobile network, and we will also show service chaining across 4 different applications. 2 applications that are not SRv6 aware, and 2 modern applications which can understand SRv6. Here we have a simple topology. There are 5 Cisco routers based on the NCS 540 and NCS 5500 families. All the routers are running ISIS protocol for IPv6 only, and all of them are able to perform the different SRv6 functions. Sometimes we will use those functions, but mostly they will do just simple IPv6 forwarding. Gnode B and user plane are always represented by 2 VPP instances, where one will encapsulate the user packet into GTP, and the second one translates GTP into SRv6. On the other side of the network, we do the functions in reverse. Firstly, we translate from SRv6 into GTP, and then we do GTP decapsulation. This approach demonstrates full interoperability with the current solution, but ultimately, when the UPF or Gnode B becomes SRv6 capable, then GTP will not be needed at all. Here we simulate the control plane with the network service orchestrator, but this orchestrator only provisions on the Gnode B and UPF. It is not touching anything else. It does not touch any router, it does not do any provisioning in data center to create new service chaining. Everything needed to achieve this is encoded in the packet header itself in a list of segments ID. Instead of using actual user devices and real application traffic, we use a traffic generator and we will measure packet latency. First scenario shows the enhanced mobile broadband service. EMBB is just pure internet access, so we need to use the best path through the network, which is typically indicated in the IGP metric. So here we will just do simple GTP translation into SRv6 without any SRH. And for forwarding packet, we will use the shortest path through the network. Here we can see how the GTP encapsulation looks. It just takes the original packet from user device, cell phone, and encapsulates it into another IP packet where the source address is the address of the Gnode B and the destination is the UPF. The most important field in GTP is the tunnel endpoint ID, TID, which is a value used to identify each PDU session. The segment ID, or SID, in SRv6 is a very powerful concept. It looks like an IPv6 address as it is 128 bits long, but it is not an IPv6 address, but a functional identifier. It has basically 2 parts. The first part is a locator, which is typically the routable portion of SID, and second part is the function identifier. This function can also have one or more arguments. We are going to use this concept to encode the TID into the SRv6 function. So in our example, the locator field 2000:8 is identifying node in the network. 89:0 is the function, and the last 32 bits of the SID are used to encode TID. In this case, the TID is 10 or A hexadecimal. Here is the network topology and the NSO graphical frontend. Right now, there is no traffic running. So the first step we have to do is to create the EMBB slice, which means to create a default policy on both ends of the network that translate any incoming GTP into SRv6 and sends it over the shortest path. Now the user attaches the network and the traffic starts flowing using default EMBB slice. It's very simple. Here on this chart, we are measuring the latency of the traffic, and we can see the latency is approximately 32 milliseconds. But let's say there is a second user who requires a low latency service. Let's start second service then. But as there is only one slice in the network, our new service is using that same slice. This means our low latency service still has a long latency. So we need to create a low latency slice. But remember, our touch points to control the network are only the G-node-B and the UPF. So slice creation actually means we create new SRv6 policy on both ends of the network. And once this new policy is created, we just need to steer the new service traffic to use the new policy. And immediately we see the result. I cannot stress enough, we didn't touch anything in the network. We didn't create any channel in the network. We only created a new policy on the G-node-B and steered the traffic using that policy. This is our traffic flow, and right now we are doing traffic engineering using the SRv6 header. So encapsulation of the original packet actually consists of two SIDs. The first SID identifies the forwarding function of router 4, and the second function identifies the same end GTP function in forwarding plane. This way, we will ensure the packets will go to router 4 along the shortest path and then from router 4 towards the UPF. This is sufficient to define the low latency path. We have seen how traffic engineering is done, but we can also use the same concept not just for the network itself, but also assigning individual SIDs to virtual machines or containers or even applications. By doing that, we can ensure that a packet goes through a particular application or set of applications in a specific order. In our small data center, we have 4 different applications. 2 applications do not understand SRv6, so we need to use SRv6 proxy function in either VPP or Linux. But the other 2 applications, IP tables and Snore, are already modified to understand SRv6, so they are able to act upon the inner packet. When each application has its own SID, this allows us to add the SID to the packet header and thereby steer the packet through a specific service chain in the desired order. So the control plane instantiates policy to G-node-B using 3 SIDs. The first SID, 2001:0:F::A::, identifies the QoS application in a container. The second SID, F::B::, identifies a DPA application, and the third SID is our known NGTP function on the user plane. So we select 2 services, QoS and DPI, and use NSO to update the policies on the G-node-B. The immediate result is an increased latency of the service and also some packet drops, both of which are caused by QoS shaper in the container. We can simply modify the parameters in a QoS container to increase the shaper size. And once we change the shaper, we immediately see decreased latency and decreased rate of the drop packets. This is our DPI container, and it actually shows two streams coming through from the UE to the packet core. One of them has a destination port 445, which is very often used for various types of attack. So we might want to filter it out. We can change the service chain entirely. We will start with the firewall, then we do packet inspection, and the QoS function will be last. We apply the new service chain, which is just new setlist, to the gnode B. There is zero configuration in a network, and there is a zero configuration in a data center to create new service chain. The result is that we immediately start dropping port 445 traffic, and so our QoS function gets less data. Consequently, there is no longer any queuing, and therefore the latency is back to 32 milliseconds. Let's check the DPI. Because now it is behind the firewall, it shouldn't show any packet towards port 445, but only legal traffic. We have shown how the old GTP protocol can be replaced by SRv6. And once we have SRv6 encapsulation, we can do many very interesting things with the packet or the flow. Here we demonstrated a very simple way to create various network slices with different topologies and different SLAs. Then we have shown a very flexible service chaining method using modern SRv6 capable applications or legacy applications with proxy functionality. All this can be done by encoding simple instructions called the SIT directly into headers of the packet at ingress of the network. The same technology can be used to create layer 2 and layer 3 VPN with exactly same properties. If you want to know more about segment routing, you can find a lot of useful information on the segmentrouting.net page or follow us on social networks. Thank you very much for your time today, and I would like to point out that this demo wouldn't be possible without the many passionate contributors. Goodbye.